Hello guys, welcome to our lesson. Today's topic is the magnetic force between current carrying parallel conductors. This is the goal of the lesson. At the end of the lesson you'll be able to explain Ampere's experiment, describe and calculate the force acting between current carrying parallel conductors, and describe Ampere's force law. It was the autumn of 1820. Christian Oersted had just discovered the connection between electricity and magnetism. Meanwhile, a French physicist named Andre-Marie Ampere was experimenting with some wires, trying to learn more about the connection between currents and the magnetic field they create. He took two parallel wires, ran a current through both of them in the same direction, and the wires attracted each other. And when he ran a current through both wires in the opposite directions, the wires repelled each other. Studying this strange force between the wires led Ampere to discover one of the most fundamental laws of electromagnetism, what we now call Ampere's force law and Ampere's circuitry law. Pay attention to this demonstration one more time. In the first picture, current is zero, so there is no force between the wires. And in the second picture, current in the wires are in the opposite direction, so they repel each other. The current in the wires are in the same direction in the third picture, so they attract each other. But why do the wires attract and repel each other? It's easier to answer if you look at one wire first. Like we talked about in our previous lesson, the current running through a wire generates a magnetic field. And again from the last lesson, the wire will deflect towards the weaker magnetic field regions. Since a current in a conductor produces its own magnetic field, when two conductors are placed near to each other, each wire will exert a force on the other one. This is the situation when wires have currents in the same direction. From the first right-hand rule, we can illustrate the magnetic field lines for the both wires. For the first wire, magnetic field lines are directed from you into the page at the right side of the wire. And the magnetic fields are directed towards you out of the page at the left side of the wire. And for the second wire, the magnetic field lines are directed the same. The region between wires has magnetic fields which are in the opposite direction. So the magnetic field in this region is decreased. As we know, the wire will deflect towards the weaker magnetic region. That's why wires are attracted in this situation. But this is the opposite situation. We have the wires here which have currents directed in the opposite direction. Again, using first right-hand rule, we can illustrate the magnetic field lines for the both wires. Magnetic fields in the region between the wires are in the same direction here. So the magnetic field in this region is increased. That's why the wires will repel each other in this situation. Okay, but what about the magnitude of the force between wires? Consider two long, straight parallel wires separated by a distance of d, having lengths of L1 and L2, and carrying a currents of I1 and I2 respectively, in the same direction as shown in the picture. The force on the wires is created by the magnetic field produced by the other wire. Let's use the notation of F1 for the force on wire 1 due to wire 2, and F2 for the force on wire 2 due to wire 1. Wire 1, which carries a current of I1, produces a magnetic field of B1 at the position of wire 2. The direction of B1 is perpendicular to wire 2. The magnitude of B1 is calculated as follows, and the magnetic force exerted from the magnetic field of wire 1 can be calculated as follows. And you see here B1, we can substitute the expression for B1 into this equation, and we get this kind of expression. Now, if we arrange the terms, we can get this kind of equation. So force 2 is equals to mu0 times currents which flows in the first and the second wire, divided by the 2 pi d, this is the distance between wires, and multiplied to the length of the second wire. So similarly, you can calculate the force exerted on a first wire. So basically, these equations are called Ampere's force law. And analyzing this equation, we can state the followings. It's obvious the magnitude of F1 and F2 will be the same if the magnitude of the length is also the same. Ampere's force law states that the force of attraction or repulsion between two wires is proportional to their lengths and to the intensities of the currents. And also, force between wires is reversely proportional to a distance. Also, we can write Ampere's law as follows. Here we have a force per unit length, and it's equals to this constant mu0 over 2 pi multiplied to the currents and divided by the distance. Somehow this is similar to a Coulomb's law, the force between charged particles. Now this is the end of the lesson. If you like our lesson, subscribe and share.